1.1, the Schrodinger equation. So we have classical mechanics and quantum mechanics. Classical mechanics, all the equations we know for classical mechanics is simple. Velocity is displacement over time, or the first derivative of displacement with respect to time. That one. And momentum is mass multiplied by the velocity. Kinetic energy is half mv2. Force is mass multiplied by acceleration. All is classical mechanics. We can predict the motion of any objects around us easily using those formulas. Another formula for the classic mechanic is force is negative derivative of the potential energy, first derivative of the potential in respect to this position. Okay, now how do I prove this? So let's just look at that. Force is equal to negative first derivative of this is potential energy divided by dx. So we know that according to the conservation of the energy, EK is or potential energy is equal to negative change in potential energy is equal to negative change in kinetic energy. You already know that from the conservation of the energy. So changing potential energy, according to what we have, we can, if the change is small, it can be done like notation for dV, right? This is the change in potential energy. So instead of that, I can put this V is potential energy. I can put, so I have a negative, right? So negative and negative become positive. Change in kinetic energy. Respect to X. I know the kinetic energy is half mv2. So it's half v power 2 divided by dx. Now, just taking derivative of that, so mass is constant, half is constant, it can get out of this derivative, right? And I just have a derivative of v, which is what my velocity, right? Divided by derivative of that. So you know that v power, the derivative of that is going to be power, just power rule. Power in front, power minus 1. So 2 v and derivative of the whatever is under power, dv dx. So this is the derivative of that. And this is just simply power rule. Power in front, power minus 1. So here, the derivative of whatever it is under the power, dv dx. So 2 and 2 cancel. Now what do we do? Here, I can multiply this one by dt and divide by dt. No change is happening, right? I'm just multiply this one by 1. So I have m here, v, velocity. I can exchange dx and dt, right? I can say that dv over dt. And then here is dt dx. So this one, I know dx dt is velocity, so it's going to be dt dx. So I know velocity is dx dt, changing displacement, the first derivative of the displacement respect to time. The 1 over v is dt dx, right? Just reverse both sides. Like if the denominator here is 1, reverse it, and you have that. So dt dx is 1 over velocity. So I'm just writing everything. dv dt is, multiplied by 1 over velocity. So velocity and velocities cancel. And look what we have. Derivative of the velocity over time, respect to time, is acceleration. So it's ma. So see, the force, I proved that is equal to ma. So we can kind of, this equation is right. So force is a negative derivative of the potential respective position. Here instead of the force, you can, so ma, a is second derivative of the x respective time. equal to negative, again, for the derivative of the potential with respect to position. Okay, so these are the equations related to classical mechanics. We already knew that. Now, but quantum mechanics approach is different. We need to define a wave function phi. So this phi depends on position and time. As you see, it's the function of the position and time. Let's just look at this equation. IH bar, which is the Planck constant, the derivative of your wave respect to the time, the first derivative, equal to negative Planck constant power 2 divided by 2m, second derivative of wave respect to x, plus, again, potential multiplied by rate of wave. Let's see what are these terms, the unit of each term here. Planck constant. So here, let's just look at the IH bar, d phi dt, right? For a second, don't worry about the unit for the phi, because in each of these terms, the phi exists, so the unit kind of cancel from all of that. You just take care of the h bar. So the Planck constant is a joule second. The unit of that is joule second, and here is second here, right? We don't worry about that. So as we know, this is the unit of that is joule. This is energy. All of these terms should be energy. I can prove it for h bar again. Just knowing that about joules again, this is, let's say, kilogram, and this is meter power 2, and h bar again is joule. So you can denote that the joule here is half mv2, right? M is kilogram, half m, v power 2 is meter per second is velocity, so is that. So you use that, you simplify something. Again, you need to get to the conclusion that the unit for this term is energy. Also, this one, V is energy, right? So that's cool. Just erase that. Here, again, we define a particle that is constrained to move into one dimension. Just see on all of this equation, we will talk about it, x. We talk about just one dimensional movement. So the particle is under the force F, and it's just influenced to work on x direction. I is a square root of -1, everyone, I believe, know that. The I is imaginary number, is square root of -1. H bar is Planck's constant, 1.054573, multiplied by 10 power -34 joules second. The Schrodinger will play a role logically analogous to Newton's second law. It will give us initial condition. If the initial condition is given to us, like at time 0, when the time is 0, that we have a wave phi x. So we can use this Schrodinger equation to determine the wave at all future times. In classical mechanics, Newton's law determines x for future time. So in quantum mechanics, we talk about the wave function. In classical mechanics, we talk about the position of the function. So that's the main difference, and those equations are different for both of these two.